No, no quiz, just a test. Let's just go over this as a quick review of what we did last time. So I'll just do version A. Again, they were very similar, so. One, state the equation in the fundamental theorem of for line integrals. What was that equation?
The line integral of the gradient of f dr is equal to the vector field evaluated at b minus a. Yeah. Given that some parameters.
Right, there was blah blah blah, but I just wanted you to state the equation, so you didn't have to talk about it.
Can you write the big F with the derivative?
Huh?
No.
Big F would mean what?
F of b minus f of a.
Yeah, but what is big F?
Oh, that's what I remember.
No, instead of the gradient of that. If you wrote big F instead of the gradient.
If you wrote big F here,
That's the
Yeah.
word.
Yeah.
no, that would be wrong.
Let's assume that they're equal. Okay.
Yeah, that's what you put.
Because the
that's
theorem
what-
is only true if it's a gradient function. If it's some general vector field, this is not necessarily true. It's literally only true if it's a gradient field. What does it mean for F to be conservative?
The word has to be 0 and is independent. Independent of path and work is 0.
Like it has a potential function.
It has a potential function, is how I would express it. That means this is equal to the gradient of some vector field.
So if you wrote independent of path, that's wrong.
If you wrote what is independent of path?
The vector field. Well, like f
If-
is
if-
independent of path, and then
You write
the work.
this. If you wrote that, I'd give it to you.
No.
What if
If you wrote,
I said that the
if you
work
wrote
was 0.
this, then no.
Okay.
What if you wrote?
And you also wrote that the work was 0.
But you'd have to write this particular integral is independent of path, then the f is conservative.
What if you wrote f is defined as p comma q given such that the partial of
Then you wouldn't answer the question because I never gave you any conditions on f, how many variables it is, what dimensions you're in. I just said in general, what does it mean for f to be conservative? It means it's the gradient field of some scalar function. Which this works for any dimensions, right? It's a general form.
Just like puts that as
Yes.
So if you describe it like in terms of work, like it's the same amount of work regardless of the path. Like would you?
Like you had space to write all that?
Yeah.
You wrote, it's the same work regardless of the path. You wrote that whole thing out. I'd give you if you explain it correctly. But I think to write down that sentence, I don't know how you'd fit that. You'd have to say something like, the work to move between any 2 points is the same regardless of the path taken. Like if you could fit that sentence there, then sure. So what about 3? So here I specifically said it is a, and then there's the comma that became a period again. I specifically said it's a 2-dimensional function where each component has 2 variables. What equation would you use in that case to check if it's conservative?
The partial of.
So this means that f is specifically now a 2D vector field. What equation would you use to say it's conservative?
Partial of p with respect to y.
This means the partial of p with respect to y must be equal to the partial of q with respect to x. That's the equation we're using. That only applies to 2 dimensions, right? If it's 3 or more, you'd use a different set of equations. Okay. So those guys are just the concept questions. You didn't really have to calculate anything. But now in problem 4, we have to start computing stuff. So it says assume these guys are conservative, find their scalar potential functions. So for part A, our f was 2xy comma x squared. How did we find the potential function?
You integrate each.
Let's integrate each. So our f would be the integral of 2xy with respect to x. So that's going to be x squared y plus some constant. Your f is also equal to the integral of x squared with respect to y, which is just going to be x x squared y plus some other constant. This is the only function that shows up, so that's our potential function. X squared y plus some constant. I believe we actually did this exactly the same example in class. But we went further with it. What was it? So it's e to the x cosine y, comma, minus e to the x sine y, comma, 2. And you kind of do the same thing here, except you do it with three integrals. So your f is going to be the integral of e to the x cosine y with respect to x. That's just going to give you e to the x cosine y plus some constant. Your f is also equal to minus e to the x sine y with respect to y. That again gives e to the x cosine y plus some other constant. Your f is also equal to the integral of 2 with respect to z. That's just going to be 2z plus some other constant. And so you just pick all the functions that show up one time and add them together. So that's e to the x cosine y plus 2z plus some constant is your potential function. So I believe this one was the same. I gave you exactly the same vector field for both versions, but problem 5 is going to be slightly different. So now we move on to problem 5. R is the line segment from, on this version it's 2, 0 to pi over 2, 1, 2, 1, pi, 3. How can I parameterize that? So part A is to actually parameterize that.
T. First one is a T.
T,
Pi over 2 plus pi over 2 T. And then 1 plus 2T.
right? Limits,
0 to 1.
0 to 1 whenever you're using that formula. So B, it's asks us to find dr, which is just going to be the derivative of this guy. So that's 1 pi over 2, 2. C, it says find this guy, where your f is the vector field in 4b, where f is that guy, e to the x cosine y minus e to the x sine y, comma 2, and C is the r of t from here. Okay, so how do we do that?
Plug in R of T into us.
Huh?
Don't you have to plug in R of T into us?
Plug in r of t into f?
Well, like the change X for T, like put in T. Don't you have to do that?
Is that what you did?
Yeah, that's what the formula says. Like F R of T.
Sure, that is what the formula says. Is that what you would do though?
You plug the points into the little f function because it's conservative.
So it says using parts A and B or otherwise. I expected you to use the otherwise. What do we know about this function? It's a gradient field. We found its potential function, which means we don't have to actually do the integral. So if you decide to like parameterize and be plugging in and taking a dot product and doing an integral, you wasted a lot of time. It's a gradient field, which means the fundamental theorem for line integrals applies. And hopefully you got that correct in problem 1, so now you know what formula to use. This guy is simply going to be f of the final point minus f of the initial point.
Are you double penalized?
And so I'm just going to plug those points into this, and that's equivalent to me actually going through and beating this line integral to death. So I'm going to plug in x equals 1, y equals pi, and z equals 3, minus, I can forget the plus k because the k is going to minus the k. Plug in x equals 0, y equals pi over 2, plus z equals 1. Cosine of pi is what?
Yes,
Negative 1, so that's just minus e, plus 6. Cosine of pi over 2 is 0, so that's going to go away, so that's just going to be minus 2, and so that's minus e plus 1. So yeah, f was the same guy in 4b, and in 4b I had to define a potential function. It means it's a gradient field. I could just use the endpoints. The curve actually does not matter at all. The bonus is about Green's theorem, which is what we're going to do today. So let's actually jump into that.
Professor,
Yes?
what's the format of the test?
Hmm?
The format of the test.
It's going to be about 5 problems, and just doing problems like this. It will look like problems in the review, pretty much.
Is it like questions from like past finals or like the quizzes you did?
Well, kind of both. The review that I posted should be your guide. Like problems like that, you should be able to do. So problems like computing line integrals, using the fundamental theorem for line integrals, being able to find potential functions, and use them to compute line integrals, as well as the Cal 3 stuff, which is going to become super important pretty soon. But now we're going on to 13.4, which is Green's theorem. So it's a very important theorem. The vector calculus part of this course is really geared towards teaching you 4 theorems, which you're going to more than likely need in the future, especially if you're in sort of engineering and or math major. Physics majors will need it a lot too. But yeah, the fundamental theorem for line integrals was one of the theorems that are super important. Green's theorem is another theorem that's super important. We'll also cover Stokes' theorem and divergence theorem, and we'll kind of wrap up the vector calc part of the course with after we finish that theorem. You can think of all those theorems as generalizations of the fundamental theorem of calculus. You can also think of Green's theorem as a specific application of Stokes' theorem, which is going to be the next one we're going to cover. But Stokes' theorem starts to do things in 3D, so we're going to need to remind ourselves how to do triple integrals and all that stuff when we get there. But for now, Green's theorem is something that works in 2D. We're still going to need to remember how to set up double integrals, but that's pretty much it. At this point, we don't need triple integrals right here. So I'll pretty much just state the theorem for you, and we'll use it after one definition. So we're going to talk a little bit more about orientation. It's going to be very important moving on from now. So I'm going to define for you our convention for what qualifies as positive orientation in 2 dimensions. So let's see the enclosed curve. We define positive orientation as traversing C in a counterclockwise. So we're kind of going back to trig, how we used to measure sine and cosine around the unit circle when we're taking counterclockwise as the positive orientation. Right? So if you see some sort of closed curve in 2 space, and you're told that you're traveling around the curve in this direction, this is called a positively oriented curve. Obviously, if you're going around the other way, it's called negatively oriented. So you can do the same curve, but you can travel in a clockwise direction and travel it around in this direction. That's negatively oriented. Yes.
What if you're in 3 space?
Oh, in 3 space, we'll define orientation based on normal vectors. So we'll actually get to that. It's going to be very different here. So it is kind of based in this idea, but you apply the right-hand rule and then you get a normal vector, and we'll discuss that. So in 3 spaces or higher, we don't actually use a direction like this. We use normal vectors, how we're going to orient the normal vectors. And basically, if our normal vectors are pointing outside of the solid, that's positively oriented. It's pointing inwards towards the middle, that's negatively oriented. But we'll talk more about that when we get there. For now, we're just talking about orientation of a curve in 2 space. Right? Counterclockwise is the positive orientation. And it's more or less a convention. So it's just like how in physics, if you're talking about gravity pointing downward, they call that, oh, it's a negative acceleration, and moving up is positive. Right? It's just, we just use it as a convention. So everyone's sort of on the same page. So this is called positively oriented. It means you're traversing the curve in a counterclockwise fashion. Okay? So now we can actually get to Green's theorem. Due to the mathematician George Green. So it says here, let D be, let's define C. So this is again kind of going back to the bonus. Let C be a piecewise smooth closed curve. Right? So that means we can break up this curve into a bunch of little curves where their tangent vectors are never 0. We'll always know the direction that the curve is moving in at any given time. And it's closed, which means the start point and the end point are the same. Okay? And suppose C is the boundary of an open region, which we call D. Okay? So I'm in 2 space. This is all in R2, by the way, or some equivalent space. We're thinking in 2 dimensions here. Okay? So C is a piecewise smooth closed curve. The region that it's bounding is called D. Then the following equation holds. So here's what Green's theorem tells us. The line integral around the curve C of P dx plus Q dy is actually equal to a specific double integral. It is equal to the double integral over the region D of the partial of Q with respect to x minus the partial of P with respect to y. Where P, Q are functions of x and y with continuous first partial derivatives on an open set containing D. This is Green's theorem. So basically it tells you that you can compute this line integral by actually doing a double integral. And I'll discuss sort of more how this is a generalization of the fundamental theorem of calculus later after I do all these theorems, but that's basically what it says. This equation holds under these conditions. C has to be positively oriented. So let's see. So you can put that in here. It's a positively oriented meaning I'm thinking of traveling around this curve in a counterclockwise fashion. If I'm negatively oriented, I'd have to put a negative sign here. That's the only way it's going to change, based on what we discussed previously. And so that's Green's theorem. So in the bonus for the quiz, this was the equation you had to write down. And when you're defining what the pieces mean, you'd have to say C is a piecewise smooth closed curve, D is the region that it's bounding, and P or Q are two variable functions with continuous first partial derivatives on D. Okay? And that's Green's theorem. It's a very important equation, has many uses. One thing you can note, as previously discussed, we can think of this line integral as a work integral for some particular vector field. So Green's gives us an alternative for computed work. So this is called Green's theorem. It's a theorem that says under specific conditions, when your C is a piecewise smooth closed curve, right, it has to be closed. The theorem does not apply if the curve is open. So if it's a closed curve, then computing the line integral around that closed curve will be given by this double integral. And of course the idea being is that sometime computing this is very difficult, and that's a lot easier. As well as there are many applications where you knowing it's a double integral can actually imply a lot of other things. So for example, you can interpret the double integral as area, and so that can tell you a lot about how things are looking geometrically. Okay, so let's actually do some examples. Write that down, that's very important, and you have to remember this. And you can also remember that this guy is actually equivalent to this guy. So if you wrote the equation either using this or this on the quiz, I would have given you points. Example. Evaluate this line integral on C of y cubed dx plus x cubed plus 3xy squared dy for C is the positively oriented unit circle. A. Doing this directly based on the definitions of line integrals, and B. By using the double integral way of Green's theorem. So we're going to actually compute this in two ways. So you're going to see that they're giving you the same answer in this particular example. So compute that line integral when we're traveling around the unit circle in a counterclockwise fashion. One, based on the original definition that we know for line integrals, and two, based on using that double integral in Green's theorem. Okay, let's do A. What do we do? parameterized. So what's going to be the x? Cosine t. The y? Sine t.
Right, Professor, how do you know that x is cosine t?
It's a unit circle. Go back to lecture 2.
C is a
We-
part.
We spoke about parameterizing circles, straight lines, and general functions.
Oh, you
Circles
mean
are always
circle.
parameterized by
Okay,
r
I didn't
cosine
see
theta.
the word, okay.
Yeah, it's a unit circle.
Okay, okay.
Okay, so r is 1, and so that's the parameterization. Limits here,
0 to 2 pi.
it's the entire circle, so it's going to be 0 to 2 pi. Now we need to find the dx, which is going to be minus sine t. Find the dy, which is cosine t. And so we're going to plug that in. So the integral on this guy is going to be the integral from 0 to 2 pi of, now we're going to plug in the parameterizations here. So our y was sine, so this is sine cubed t times dx, which is minus sine t. Put the dt's at the end. Plus x cubed is going to be cosine cubed plus 3 times cosine t sine squared t times dy dt. So you can also think of this equation as giving us the work performed by moving around the unit circle if our environment is given by the vector field y cubed comma x cubed plus 3x squared xy squared. Okay, let's actually do that then. At this point now, it's kind of just crunching through the Calc 2. Let me recopy this. So this is what would this be? Cosine to the 4t plus 3 cosine squared t sine squared t. Okay, how do we do that? Ideas? Yeah?
You can say that the cosine squared in the last of the things is the same thing as 1 minus sine squared t. Or we could just I guess do a u substitution.
And substitute what?
I'd break it up
Could be a
into
factor out of sine
pieces.
squared plus cosine
Use the
squared.
half angle formula for the first two, and for the last one, pull out the.
Use a half angle formula. Exactly. So this guy, how would I rewrite that using half angle formula?
1 minus cosine 2t.
Isn't that one, what do you want with it, 1/4?
Right, so we're going to think of that as sine squared squared. Use the half angle in the inside. That's going to be 1 minus cosine 2t. Plus, think of this as cosine squared squared. That's going to be 1/2 1 plus cosine 2t. This guy, 3 times, so that will be 1/4 times 1 plus cosine 2t, 1 minus cosine 2t dt. Okay, now what? Let's just actually go through the algebra here and expand these guys. Let's see what we get. So you square this, you're going to get 1/4 times 1 minus 2 cosine 2t plus cosine squared 2t plus quarter times 1 plus 2 cosine 2t plus cosine squared 2t plus 3 over 4, and that'll be 1 minus cosine squared 2t. Do any of these guys cancel? I think this is minus a quarter. So if I expanded this, I would get minus a quarter, right? And then plus a quarter. So those two will die. Here I would get plus 1/2 cosine 2t plus 1/2 cosine 2t. So that would give me cosine 2t. Here I'd have minus a quarter cosine squared 2t plus a quarter cosine squared 2t, so those guys just kill each other. And so here I would have plus 3 over 4 minus 3 over 4 cosine squared 2t, which I'm going to just apply the half angle formula again, write that as cosine 4t. And now what? I can ignore this, that's going to give me 0 because I'm integrating on 0 to 2 pi. I can also ignore this, that's going to give me 0 because I'm integrating on 0 to 2 pi. And so basically this just boils down to the integral 3 over 4 minus 3 over 8 dt. So that's just the integral from 0 to 2 pi. Of what is that? 3 over, is that just 3 over 8?
Yeah.
So what does that become? Yes?
For the 2 cosine 2t, if it's negative 1/4 times negative 2 cosine 2t, it doesn't cancel with the other 2 cosine 2t, does it?
Which one?
2 cosine 2t, it's negative 2 cosine 2t times negative 1/4, and then, so that's positive, so then it can't cancel with the positive 2.
Yeah.
Oh, this is, oh yeah, that's a negative sign. So we're missing a term, right?
Yeah, it's supposed to be,
Let's just add it in the last part here. So what do we have here?
Isn't that the cos 2t at the beginning? Yeah.
is it? Oh, okay.
Yeah, it's the cosine.
Okay, okay, alright, oh, yeah.
Okay. Okay, does everything else look fine?
Yeah.
So this we use here, let's just double check, that's the half angle formula. I'm applying here, and that's squared. Half angle formula applied here, that's squared. Apply the half angle formula here for the cosine, and here for the sine, and that's a quarter. It's minus a quarter, plus a quarter. And I expanded this guy, 1 minus 2 cosine 2t plus that, 1 plus 2 cosine 2t plus that. 3 over 4. Here I use the difference of squares, so I get that. So this is minus a quarter plus a quarter, so that's gone. I have 1/2 cosine 2t plus 1/2 cosine 2t gives me 1 cosine 2t. I also have minus a quarter this plus a quarter that, so that's gone. Then I have 3/4. This should be a plus here, right? No.
You're right.
Then I have 3/4, that's the plus 1 here, minus 3/4 this guy, and what?
You say you have to do half angle formula.
Yeah, so it's 3/4, which gives me here, and then I take 3/4 of that, and then I apply the half angle formula again.
Yep.
That gives me cosine 4. And that's right?
Yeah.
And then, so now, right, integrating cosine 2t from 0 to 2 pi is going to give me 0. And so I only have that 3/4. Integrating cosine 4t from 0 to 2 pi is also going to give me 0 when I multiply out, so that's gone. And so I have really a half times this. And so I have 3/8. And so now I'm going to plug in 2 pi. Right, so that's 3/8 t from 0 to 2 pi. And so that's going to be what?
3 power of 4.
3 power of 4. God, I hope that's correct. But of course, the point of this example is for me to show you that the double integral should be a lot easier. Because that's going to be annoying. Okay. So this is going to be us doing it the other way, so we should get 3 power of 4, hopefully. So this is going to say that this guy is actually going to be the double integral over d of partial of q with respect to x minus partial of q with respect to y dA. So what is going to be the q? What was our q? I erased it. What was our q? Okay, so I'm going to partial that with respect to x. 3x squared plus 3y squared. Right?
Couldn't it be 3, like, what are you doing?
I'm taking the partial derivative of the q with respect to x. Minus, now I'm going to take the partial of the p
So 3x squared
with respect to y.
3y.
So that's 3y squared. So that goes away. And so that's just dA. I was wondering why I have the feeling that I did something wrong. I actually copied the wrong problem. The curve. I copied the curve for this from the other example. Doing a rookie mistake. It's a lot of times when you're in the tutoring center, and a lot of times students are getting things wrong. I think I'm doing everything right. It's like you just copied the wrong problem. You're doing problem 2 instead of problem 3. Okay, so let's hope we actually get the right thing. So how would you set up this region D? It's the unit circle. How do you actually set that up?
R goes from 0 to 1.
R goes from 0 to 1. So you're thinking of using cylindrical.
Yes.
And theta goes from 0 to 2 pi.
Yes.
So this is actually going to be a bit more complicated than I actually wanted it to be, but it's already looking a lot easier than this anyway, so that we kind of lucked out here. And so this would be 0 to 2 pi, 0 to 1. X squared would be?
R squared cosine squared.
R squared cosine squared theta. My dA would be?
R d theta.
R d theta. So yeah, that's more complicated than how I set up the example originally. It was just supposed to be a constant here. We're just supposed to use the area of the circle, but hey, whatever. This is actually not that bad. So we integrate this, we'll get r cubed.
What happened to the other r? Isn't it?
R cubed.
Oh.
Yeah.
So we integrate 3r squared, so this becomes what? 3/4 r to the 4th. Cosine squared between 0 and 1. And 0 to 2 pi. So I think we can fit it here. So I plug in 1, if I plug in 0 I kill everything, so I plug in 1 I would just get 3/4 times 0 to 2 pi of the cosine squared. So the cosine squared, I would use the half angle formula. 1 plus cosine 2 theta d theta. That guy's going to give me 0, so I'm going to ignore it. And so this would give me 3 over 4 times 1/2 times 2 pi. So that's 3 pi over 4.
Professor,
Yes.
so the D from dA, when you were converting to the polar coordinates, dA
Yes,
would,
dA becomes r dr d theta when you switch the coordinate system. Let's do another example. So for those of you who are interested, originally, what I wanted to do was the same integral of so y cubed dx plus x cubed plus 3xy squared dy. And my c was the following curve.
That's, Professor, so where did
Yes.
those numbers come from? That original one that you did up there, the 3x squared?
Oh, I had 3 examples, but I copied the curve from example 2
So that's
for
just a
example.
random example.
So this now is an example you can try on your own. I'll tell you what the answer should be, and you can try it on your own. And then I'm going to do another example. So this is the line segment from 0, 0 to 1, 1.
So they're not the same problem, is that what you're saying?
No, my C is different, so they're not the same problem.
No, I'm not talking about that one, I'm talking about the problem that you just did. Is it the same, remember you said we were gonna do the same problem? One, we're gonna do it in the old way, and two, using reason.
We already did it 2 ways.
yeah.
It was? So where did the 3x squared come from though? That's what I wasn't, what are you saying that you messed up?
What are you talking about?
That's a derivative of q, derivative of the y component in the
Let me finish doing this. Then we went from 1, 1 along to 0, 0 along y equals x cubed. So that was the original example. That's the example I meant to do. And you can try this on your own. And the answer should be, if you actually do it correctly, which when you do it both ways, you should get the same answer. The answer, I think I did, this was negative a quarter, I think.
Professor,
Yes.
so right here, you get 3/4 r to the 4 cosine squared theta 1 to, okay, that part I got it. And the next part, how do you get 1,
Well, I plug in 1 here,
uh-huh,
so that's just 3/4 cosine block.
okay,
And then I plug in 0, which is nothing.
okay,
And then, so I just have 3/4 cosine squared.
cosine.
Cosine squared, I use the half angle formula.
Half angle
Okay.
formula. Okay, then how do you integrate that over sine theta, right?
Yes, then well, I didn't actually integrate, we know that if you're integrating cosine
2 theta,
n theta dx over any multiple of the period, this is always going to give us 0, so we don't waste our time. That's something you discussed in Calc 2.
oh,
If you're integrating a sine or a cosine over a period, the positive part and the negative parts will kill each other.
oh, okay.
So I don't actually do that. I just know, I know the period of this is pi, so if I'm integrating between 0 and 2 pi, that's going to give me 0. So I just ignore that part. And so I'm really just integrating a half.
Okay,
So that gives me a half t, and I plug in 2 pi, so that's a half times 2 pi.
2 pi, oh, okay.
let's do another example.
Wait, are we not gonna do the one you gave the answer for?
Yeah, you do that on your own time. I'm gonna give you another example.
Okay.
But you try this, you should get minus a quarter.
Yeah, I'm just not sure how to set up C. I understand what it is, I don't know how to set it up in the problem.
Oh, well that's, okay. How would you set this up?
We
Let's
have to
talk
do
about
it
that.
twice.
Huh?
We have to set it up twice.
If you're doing it directly, you would have to set up something twice. So if you're doing directly, you would actually do it in two versions. So you do a C1, you do an integral along C1, where that's the line segment. And then you do an integral over C2, which is going to be the cubic. And then you add them, the answers together.
But even if we do the other way, don't we still have to do it twice?
No, with the double integral, you only do it once. So with the double, if you're doing the double integral way, then what happens is you have this region. You have a region that looks like this.
Okay.
And you set that up using a double integral, and it's going to be one double integral. So it's one region, so you'd only need one double integral. But if you're doing it directly along each path, you need two to do it directly. I think in my next example, I'm just going to ask you to compute something. Maybe I'll put this exact same problem on quiz next week. Or the following week. See who actually tried it at home. Okay. So here's an example. Always see this. Tan inverse of x plus y squared dx plus e to the y minus x squared dy. So compute that, where c is the path shown. So here's c. I'm actually going to describe it with a picture. So of course that's the top half of the annulus centered at the origin. And I'm traversing this. So how would you compute that? How do you do it directly? Like no. Like I'm not even gonna try. Nah, I wouldn't. Yeah, right. So directly you'd have to split it up into like one curve, two curves, three curves, four curves. You need to do 4 line integrals in order to compute that guy. Right? But of course, this is actually a very nice region that we can describe with a single double integral. So instead of, if I care about computing the work for this vector field around a surface that looks like this, I would actually apply Green's theorem. By Green's, that line integral is going to be equal to my double integral over d, which is the region here, of the partial of q with respect to x minus the partial of p with respect to y. Where this guy here is my p, which is always going to be the coefficient of dx. This guy here is my q. So that's going to give me the following. Partial of q with respect to x is what?
2x.
Well, minus 2x. Minus partial of p with respect to y?
2y.
And dA. Okay, so how do you set up that double integral? How do you set up this region over my limits b?
Q x. Okay, negative 12. And the dx would be 12.
So what would that be? What would that setup be? So you'd switch to polar, so this would become r dr d theta. And so this guy would be, I can take out a -2, and so this guy would be r cosine theta minus r sine theta. Limits.
1 to 3.
Yep, 1 to 3.
On the outer limits, what is it?
0 to
Zero to
pi.
pi.
0 to pi. On the inner limits?
1 to 3.
No.
Is it not 1 to 3?
Is it 1? What number? 3?
1 to negative 1.
1 to 3.
Oh, 1.
And so now we just have to compute this one double integral instead of doing 4 line integrals. So what would we have here? Oh, I have space for this. So this I can really just think of as, this is 0 to pi, this is 1 to 3, this is just r squared times cosine theta minus sin theta. That'd be fair. Right, I just factored out the r, so that's r squared. Integrate with respect to r first. So that guy would give me r cubed over 3. Between 1 and 3.
Question.
Yes.
So you figured out -2. Why is it minus r sine theta?
Plus. So now you plug in 3. So what do you get? Just get, well, you get 27 divided by 3, so you get 9. Minus, you plug in 1, you just get a third, right? And so that's -2 times 9 minus a third times integral of cosine is sine. Integral of sine is minus cosine. And we're going to plug in 0 to pi. Plugging in pi or 0 into sine will always give us 0, so ignore that. And so this is going to be -2, 9 minus a third, times cosine of pi is -1, so that's +1. And cosine of 0 is also 1, so that's another +2. Okay, so that becomes what? What's 9 minus a third?
26 over 3.
26 over 3.
Lesson.
Whatever is 4 times 26. Just in time. Okay, and that's basically Green's theorem. So it's just another way of computing a line integral when we know we're on a piecewise smooth closed curve in R2.
Professor, this won't be on the test though.
No, the test ended with what we did last Thursday. It's fair for a bonus problem.
Oh, there's a bonus on the test too.
Yes. Okay, we'll end there. I'll see you guys on Tuesday. So yeah, like I said, the test is going to be around 5 problems, similar to what's on the review. What? There's a like a PDF on the website.
No, there are like spring 2005 finals.
Not for the test 1. That's for the other one. Yeah.